In this class, we shall discuss the S.I and Gaussian unit and dimension of the three vectors, namely vector E, vector D and vector P, where let us define that vector E stands for the electric field, vector D represents electric displacement vector, and vector P is called the polarization vector, or simply polarization. Let us first mention the interrelation between these three vectors, both in the SI system as well as in the Gaussian system, in order to get a clue of how they would be related, what should be their units and dimensions. So the interrelations here we shall write the SI relation, and here let us write their relation in Gaussian system. First the SI, where vector D is related to E and P through this equation, and in Gaussian system the relation that exists between these three vectors is these relations give enough clue about the unit and dimension. Namely, in SI system we note that the dimension of D should be equal to the dimension of E should be equal to the dimension of P, where the third bracket stands for dimension. And in Gaussian system it follows from this relation that the dimension of D is equal to the dimension of E, which is again equal to the dimension of P, because 4 pi has no dimension as well as unit. So things are different in the two systems, but in both the systems D and P have same dimension. So let us write things clearly. It follows from this discussion that D, epsilon 0 E and P in SI system should have same unit and dimension. Clearly, dimension of E differs from the dimension of D and P, but in Gaussian system D, E, P all have same unit and dimension. What we shall do now is to find the unit and dimension of the quantities E, D and P in both the systems. Then these statements would be checked. So let us make a chart as follows. We shall write down the quantity here in this column. Then we shall write down the unit and then the dimension of the quantity in SI system here, And the same thing in Gaussian system here. To start with, let us find the unit and dimension of the electric field vector E in both the systems. And after we get it, we shall fill this chart. So let us begin with unit and dimension of E in SI system. We shall start our discussion by quoting Coulomb's law. And this is it. So F by Q is 1 by 4 pi epsilon 0 Q prime by R square, which is defined as the electric field. We are considering scalars for simplicity because our interest is to find unit and dimension, and so we need not focus on the vector character of quantities. Considering only the scalar part, we can find the unit and dimension of these vector quantities. So this is the prediction of Coulomb's law. It is clear that Coulomb's law tells us that the unit of E is Newton per Coulomb. That follows from this expression of F by Q. F is force, the unit is Newton, and Q is charge, the unit in SI system being Coulomb. So this is the unit of E that we got. Let us quote this relation once again. So E is F by Q, which is Coulomb's law. Multiply numerator by length, the denominator also by length, and then what we get is energy or work. Force into distance is work or energy by Q into L. So another unit of E that we get is unit of energy or work is joule, and the unit of charge, that is Q, is Coulomb, and that of length is meter. Again, let us recall a very popular relation. I square RT is equal to amount of heat produced, that is H. Let us break it in this way. IT into IR is equal to H, and IT is Q and IR is V. So Q into V is H, another extremely popular relation. And let us write down the unit to get Coulomb into volt is equal to joule, which gives us joule per Coulomb is volt, and this we can use here. That gives us the unit of E to be so joule per Coulomb is volt, so it is volt per meter. So this is the unit of E. And now to find the dimension, we once again write E equal to F by Q. So the dimension is mLT to the power minus 2, which is the dimension of force, and the dimension of Coulomb, let us write it in this way, as is done in the SI system. So it is ml t to the power minus 2 C inverse. And taking into account the relation that current is dq dt, we can write ampere, the unit of current, is equal to Coulomb by T, which is second. So C is equal to A into T. And therefore substituting AT for C here, we get an alternate prescription or form for the dimension of E, which is ml t to the power minus 3 A inverse. So the dimension of E is either this one or this expression. And let us fill the chart. So the SI unit of E is Newton per Coulomb or volt per meter. And the dimension is or let us now find the unit and dimension of epsilon 0 E. So unit and dimension of the quantity epsilon 0 can be obtained in SI system starting from Coulomb's law, according to which F equal to 1 by 4 pi epsilon 0 q prime by r square, which gives so the unit will be Coulomb into Coulomb, so it is Coulomb square. Unit of force is Newton. Unit of r, that is distance, is meter. And therefore the unit of epsilon 0 E will be unit of epsilon 0 into unit of E, which is Newton per Coulomb. And therefore we write that here to get Coulomb per meter square. So this is the unit of epsilon 0 E, and the dimension that follows from here is m square is length square. So when it goes up, we have L to the power minus 2 into Coulomb. So this is the dimension of epsilon 0 E. Let us fill up this chart. Epsilon 0 E has unit Coulomb per meter square and dimension L to the power minus 2 into Coulomb. Let us next find the unit and dimension of E in the Gaussian system of units. So let us find out the unit and dimension of E in Gaussian system. And let us start with the Coulomb's law in the Gaussian system, which has the form q prime by r square. So let us write the scalar part. Now in Gaussian system, Q is quoted or measured in StatCoulomb or ESU of charge. And let us find the dimension of StatCoulomb in Gaussian system. So it is so what we get from here is StatCoulomb is equal to F into R square under root. Now put for F, which is force, mLT to the power minus 2, and R square is L square. So this is m to the power half L to the power 3 by 2 into T to the power minus 1. An important relation that we'll use over and over again. Now it follows from Coulomb's law that F is so F by Q is Q prime by R square, Q prime being the source charge, and by definition this is the electric field. So from here we get E is Q prime by R square. Putting the units, we have StatCoulomb by centimeter square. So this is the unit of electric field in the Gaussian system. We have to find the dimension of E, but before that let us multiply the numerator by length and the denominator also by length to end up with the formula of energy by charge into length. Now let us use QV equal to W, an expression that we derived. So W by Q is equal to V, the unit of which in Gaussian system is Stat-volt. So let us put the units. Instead of W by Q we write Stat-volt. So this is Stat-volt by centimeter for L. So this is another unit of E. We now find the dimension by quoting this result again. And Q is measured in Gaussian system by StatCoulomb, for which we can substitute this expression which we got. So it becomes, and in the numerator we have to put for F ml T to the power minus 2. So what we get is m to the power half L to the power minus half T to the power minus 1. So this is the dimension of electric field E in Gaussian system. Let us therefore fill up the chart. So the Gaussian unit for electric field E is StatCoulomb per centimeter square. and another unit is stat volt per centimeter. And the dimension is and we note that there is no such thing called epsilon 0 in Gaussian system, so these two cells are not applicable in the Gaussian system of units. We next proceed to find the unit and dimension of the D vector, that is the electric displacement vector. We now deal with unit and dimension of the electric displacement vector D in SI system, and we take help of Gauss law in dielectric, according to which the closed surface integration or the flux of vector D is the free charge. So this is Gauss law in dielectric, from which it follows that D goes as QF by ds, and ds is the area. So the unit turns out to be Coulomb for QF and meter square for ds or area. So we have got the unit of D in SI system, and now let us find the dimension. For Coulomb, let us write C, and for 1 by meter square, let us write L to the power minus 2. So this is the dimension of D in SI system. And let us fill up the chart. So for D in SI system, the unit is Coulomb per meter square, and the dimension is L to the power minus 2 into Coulomb, which is same as that of epsilon 0 E. We now find the Gaussian unit and dimension of D. So let us write unit and dimension of D in Gaussian system. And as before, we take help of Gauss law in a dielectric written in Gaussian system, which is, so D can be written as QF by area So the unit is StatCoulomb by centimeter square. So this is the unit of D in Gaussian system. We now find the dimension. The dimension of centimeter square or that of area is L square, and that of StatCoulomb is this one, which we got earlier. We can write and this gives us so this is the dimension of D in Gaussian system, and let us put this in our chart. The Gaussian unit of D is this one. So it is StatCoulomb by centimeter square, and the dimension is this one, which is same as the dimension of E in the Gaussian system. So This is what we have, and now we proceed to find the unit and dimension of polarization vector in the two systems. So unit and dimension of P vector in SI system, and this follows from the definition of P, which is number of electric dipoles per unit volume, and dipole moment is charge into distance, and in the denominator we have volume, so it is L cubed. Simplification gives us Q by L square. So the unit turns out to be Coulomb per meter square in the SI system, and the dimension is L to the power minus 2 into Coulomb. So this is the dimension of P in SI system, and let us put this in the chart. Let us make entry of P, the SI unit and dimension of P are Coulomb per meter square, and this one representing dimension of P. We next find the Gaussian unit and dimension of P, that is polarization. So unit and dimension of P in Gaussian system as before. We use the definition, and this is Q by L square as we got. So the unit is StatCoulomb for Q and centimeter square for L square, or area. So this is the unit of P in Gaussian system, and the dimension is, putting that for StatCoulomb, so this is the dimension of P in Gaussian system, and let us put these in the chart. So it is StatCoulomb per centimeter square, unit of P in the Gaussian system, and the dimension is this one. So we conclude that in the SI system, the unit and dimension of epsilon 0 E, D and P are same. And the unit and dimension of D and P, though same, that of E is different. So we can write that E has different unit and dimension in SI system. And these are important conclusions about SI system. In Gaussian system, we see that the unit and dimension of E, D and P are same. So we can write in the next video, we shall derive and compare the unit and dimension of vectors like magnetic induction, magnetic field, and magnetization in SI system and Gaussian system.